I'm going to share that peer evaluation link in the chat box. So Suyash, you can start anytime.
Okay. Can you see my screen?
Yes.
Okay, so for today's topic, I have a paper on using BIM in construction budget, that is benefits and barriers for it. So for the abstract for the paper is this article basically deals with the documents used for creation of a BIM model with the graphic and non-graphic specification. Let us state that there exists a classification system which matches each model element with an identifier, making it possible to link such element to a budget item or several items. That makes the software able to transform construction elements into the budget units. Also, in this paper, there is a case study reflecting the analysis of a current situation using information models of two administrative buildings and link those models to construction budget, where they found out that fifth of the total budget could be predicted from automated calculations. The introduction for the paper is it is very demanding and time consuming for a worker to create a budget based on the documents such as the classification of structures. So the cost of the construction and the future maintenance may be best influenced during the pre-investment phase of construction. Therefore, it is very necessary to pay adequate attention to the stages of construction life cycle. And it is nearly impossible to meet the construction budget exactly because some expenses come into action when the construction has been finished. There is a case study of the CISAC, which is in Central Europe. They witnessed a rapid evolution of BIM in particularly all the fields of the construction and has brought new challenges to the cost management. That is BIM 5D, which strives to adapt to local customs and needs of construction modeling. There are three pillars for which BIM and cost management may share. That is, first of all, first is creation of construction budget. Secondly, cost management during construction. And thirdly, transfer of data for individual elements comprising the construction model. But this paper deals with the only the first pillar, that is creation of the construction budget. There was different literature reviews which were done in the paper. First of all, there was a Peter Smith who in his research states that development of 5D capabilities is gaining momentum and the leading edge project cost management firms are starting to realize the competitive advantage by embracing this new age approach to cost management. Secondly, there was one more author whose name was Zima, who states that creating the construction budget on the basis of BIM model data depends largely on the LOD, that is level of development of both the graphic and non-graphic part of the model. And current potential for budget creation is limited because of the cash flow during construction. Another author whose name was Darren Olson in his research states that usage of BIM cuts the amount of time needed for budgeting in fifth when compared to the traditional method, which is where someone uses all the documents to create the budget and all of manual matching of construction units, and also stated that most important of such limiting factors is precision of the model itself. There were various other literatures carried out and they found they need to be solved before PM5D can be employed in construction because of requirements for the creation of BIM and the legislative support of BIM for the public sector and requirements for professional and information technology. Now, what is a BIM requirement needed to connect to the construction budget? Detail and high quality drafts of competition are the main keys to create a successful BIM model and subsequent implementation of BIM in any environment. This can also be assured by specification in contracting documents between the submitter who submits it and the supplier of the model. Concerning the construction budget, the main document is BEP, that is BIM execution plan, and the table of parameters. So the two documents define the graphic and non-graphic information about individual construction elements. Graphic standard here refers to the foreign methodology level of development, and the non-graphic data uh, consist mainly of characteristics grouped together in a document, which is called the table of parameters. This data basically carry particular potential for usage of information model during preparation, realization, and facility management. Another thing, which is LOD, which is level of development, states that level of detail of the information model for various stages of project documentation, and is usually specified on a scale of 100 to 500. And there is one question in this paper, like, who is responsible for starting the requirements for BIM? Is it the submitter? Is it the contractor? Or is it the investor? Or is it the designer who actually creates the model? So the most meaningful proceeding seems to be when the designer, who knows how to create the model, defines the necessary parameters. The reason behind this statement is the fact that each project has its individual requirements regarding the output data. Another thing, which is construction budget. So the goal of BEAM is basically to reach a higher level of automation. That is the easiest possible transfer from the model data to the budgeting item structure. Automation or semi-automation of budget by means of data exported from the model would make the budget not only faster, but also more precise and more efficient in a better way. It is common, like, for every country to have some national classification system or some national standards. Each have their own, or at least a common structure of elements and work classification. Unfortunately, this traditional classification system only have a limited scope of use in modern work with data, where the element and items are matched in a ratio of 1:1. According to various research, people in many countries thinks that such intervention in current work process, that is making the budget with the help of documents, would cause overloading of all professionals in the construction market and bring more problems than benefits in the current situation. So basically, we need to look for a solution which meets our local needs and also allows us to use full potential of information modeling. It is essential for the future of BIM 5D to create a classification system which would bridge the gap between the design elements and price system items. Ideally, the items should match the current price system procedures to ease the transition from traditional to modern model. In this paper, there is one example where some elements are drawn as a single construction with the inner structure such as floors and walls, and the pricing software analyzes the elements identifier and matches the element with the inner structure to several items of the price system. Similarly, same process may be applied to temporary structures which are not included in the design and are considered as the secondary items, such as the concrete wall. So it can be matched with the framework and reinforcement as well as concrete. So quantities of such items can be calculated by means of running some algorithms and matched. That is, for example, with the quantity of concrete. And another thing is the analysis of current available models. Here, the CZEC Technical University in Prague obtained two information models of construction of commercial buildings. This BIM model from 2017 show buildings which are currently under construction. First one is Parkview and the second one is Praga Studios. They are designed with the same carry structure. They focused on the amount of data which can already be directly transferred from the information model to budget on 1:1 ratio. That is, element is to price item. Subsequently, element breakdowns are used as they are described. This shows the number of secondary items and their percentage in the information model. Secondary items are those items which are not depicted in the design, such as framework, reinforcement, or which are sometimes omitted by the author of the design. As a result, both these projects show slight dominance of potential for matching elements to item on 1:1 basis. Secondary items require manual correction of elements before they could be matched to price items. In this category, the best results were seen with plastering. Quantity takeoff exported from the information model did not show plastering directly, but a proper algorithm is set up to calculate the wall space with plaster, and the results were striking well correspondent with reality. On the other hand, there were some obstructions which could have been calculated by means of the algorithm or were not designed correctly. Typically, this were embankments for the groundwork. So in the Parkview project, 63% of the budget items could be matched either directly or as a secondary item. That is roughly 71% of the total construction budget. Whereas in the Praga studios, somewhat better results in the overview elements matchable, that is 1:1, or secondary item shows a total score of 69% of the construction project. This was roughly around 78% of the total construction project. So in the conclusion, they found that BEAM needs to bring more benefits than the traditional solution. And this fact needs to be verified by both expert, public, as well as the investors themselves. And it is highly improbable that the BIM model could transfer 100% of elements to price items, but we might be able to acquire a vast majority of construction elements and works in the itemized structure from the model. It is also necessary to create different identifiers with the parameters of each construction element, which will enable the automated system to transfer data from the information model to the pricing software designed. Therefore, a database of identifier is needed to ensure a possibility of itemized breakdown of elements. And here the case study has depicted the current state of data obtainable from the information model, which can be directly or indirectly transferred to budget. The case study used two current model of buildings which are under construction during the publishing of this paper. So it shows that even with current limited use of information modeling, we are capable of matching 66% of elements to price items. So, and this percentage corresponds with roughly 75% of the budget of an above ground construction. So yeah, these are all the acknowledgement and references for this paper.
Thank you, Suyash. Any question from the class? So I do have a quick question here. A main contributor to the final project cost is the labor cost. And in your opinion, what would it be the best way to incorporate the labor cost, such as productivity, in this BEAM framework? Suyash, are you there?
I'm sorry. So here we can create a database for the labor work which are considered in the no, I guess labor work can be included in the secondary items, which is kind of a temporary, and it should match with the 1:1 relationship. That is, this particular labor will be like this quantity of laborers will be responsible for doing this concrete work, or this particular quantity of laborers will be responsible for doing the steel work, or something like this.
And also, labor cost or labor productivity can be easily affected by, a lot of factors in your project, such as the sequence, right? So what would be your solution of including this 4D simulation, like how we put together a building, for example, pouring the concrete first, or doing the slabs framework for the second level first? That will make a difference in terms of labor productivity. Or putting together the drywall first, or put a fixed light fixture first. That will also affect the labor productivity for different trades. So in your opinion, can we in the future that also incorporate this 4D simulation sequence into this estimating framework?
I don't think we can include the labor things in the 4D simulation, because like it depends on the kind of work they are doing. And for example, if the work is like there is a concrete work, so it is fixed and we don't know how many labors we will require for that particular thing. So I don't think it will be possible to incorporate labor thing into the 4D simulation, 4D cost, BIM 4D.
You don't think you don't think it's possible at all, or it's just impossible for now, but could be possible in the future?
It's impossible for now, but yeah, like with the ongoing technology and rapid increase in the technology and all, it might be possible.
Okay. One thing that I want to share with, thank you, Suyash, that's really good discussion. One thing I want to share with you guys is, there's a thing called a 3-week look ahead scheduling, and there's another thing called a detailed planning or DP. Is anyone of you aware of these practices? Okay, when I was working in the industry, my boss usually tell me, schedule, what we call the master schedule, is useless at all. It's only a contractual tool, which means it's a legal tool, showing that, hey, this is our commitment in terms of the main milestones and the deliverables, and we incorporate that in the contract, the signed agreement with the owner, but we will never follow that schedule. That is what's going on, because it's so difficult, almost impossible for a planner to predict what will happen in a project. So that's why, in terms of really planning all the activities, all the laborers, that relies totally on something called a 3-week look ahead. That means, we gather together on the job site and we have this meeting to think about what will happen in the next 3 weeks. And for each of them, so like on Monday, they also have something called a detailed planning. So the detailed planning basically shows that for each of the days in the following week, we're going to think seriously how many people we need for this particular activity, how many people we need for that particular activity. And then we start to generate a realistic cost breakdown for that. So if you think about that, it can be very difficult for us to generate a solid plan at the very beginning of the project to predict the final cost of a project. And I guess that's why a lot of people still don't trust the 5D beam. It's just another way to show the information, to integrate the information, but still it hasn't 100% resolved the problem of how would you predict the future. So if you're asking me, I guess definitely there's a need there. And maybe we should rely on data-driven artificial intelligence. So let's say if we have done so many projects and we know for this kind of activity, for the previous 3-week look ahead and for the previous detailed planning, that's what we did. And there's only 10% chance that it will be different for this project. Then definitely we can reuse the knowledge and somehow integrate that into the spatial simulation given by building information modeling, like how the tower crane is moving, how the material is moving, how laborers, staff members are putting together a brick wall, not influencing each other. So if we have all the knowledge built in some kind of a model, and the model can run this 3-week look ahead and detailed planning like for many, many, many times and generate the estimate, I guess that's probably the future. It's kind of like you guys probably heard about that, 3 years ago, the AlphaGo, artificial intelligence beat human players in the Go game, right? Or the chess game, machine beat human players because they could run the simulation for many times and then find out the optimal solution. I guess in the future, for BEAM-enabled estimating and BEAM-enabled planning, we probably will use the same approach that run simulation and try to find the optimal and the most realistic estimate of that. Okay, so any question, any comments from the class regarding this paper? Very interesting paper, by the way. If no, please use the link I share in the chat box and put your comments. Okay, so now let me share my screen and let's talk about machine learning. I'm going to, there are a lot of things to talk about, but I guess I will skip the first part and talk about that next week. Let's just start with machine learning. Okay, so can anybody tell me what is machine learning? What is artificial intelligence? And how you think about them, like their definition and their application. Can anybody? Can anybody share your thoughts? Nobody? You guys just have heard about the terms all the time, right? So here's the thing. Usually we, I have to say the academia and the industry still haven't figured out a clear boundary between three things: statistics, machine learning, and artificial intelligence. In fact, for most of the machine learning algorithms or AI applications, you can find their root in the classic statistical method, such as regression analysis, right? Such as logistic, such as a Bayesian method. So this is actually really good metaphor of what's going on. We actually started to build this statistical knowledge, since 300 years ago, like maybe 200 years ago, sorry. So when people started to think about the observations in a probabilistic way, we start to develop mathematical models to describe random. So at that time, we call this thing, let's call this as a thing, statistics. And then later on, we start to think about the other, advanced models that moving from what we call parametric to non-parametric, from a structured way of modeling our data to a more unstructured way of modeling data. Then we start to give it more meanings and give it more usefulness. So it's kind of like there's crack on the wall and we call it statistic, but we add a fancy frame to the existing statistical model and gave it a different name, machine learning. So that is ML. And as you can see from this cartoon, the core of a lot of machine learning algorithms are still from the traditional classic statistical modeling approach. And then what is AI? What is artificial intelligence? If you check the word, machine learning focuses on learning or modeling. So it focuses on the algorithm development and focus on how to model the observed data. But artificial intelligence focuses on intelligence. It focuses more on the application of that, the use of that. So if you see from the cartoon, it means a crowded audience and crowded users of machine learning, and we call that AI, artificial intelligence. So think about it this way. Machine learning is the mathematical core of that artificial intelligence. And artificial intelligence is more of the real world application of that, such as facial recognition, such as voice recognition, such as driverless cars, autonomous vehicles. That is the application of the machine learning mathematical algorithms, but we call these applications AI. So this is a very rough description of the terms, but I think this is critical. This is so important for you guys to understand the difference. So how machine learning can help our real world applications and what machine learnings are helping. I have to say machine learning now is everywhere. Actually, machine learning AI has become like a national strategic priorities in many, many countries. And they can be used for example, computer vision, image recognition, video recognition. Like nowadays, if you upload your pictures to Google Photos, it recognizes your face immediately and can tag your face in all the pictures automatically. It recognizes the thing, right? So for example, if some construction workers are doing unsafe things on a job site, this computer vision algorithm can recognize this is unsafe and give a warning. So it's very similar and with human ability. And I have to say, it's better than the human ability. There's a context called the image detection context. Before 2017, human always outperformed machine learning algorithms, but right in 2017, machine learning algorithms actually outperformed human beings in terms of image detection. and their accuracy is almost perfect, like 99% nowadays. And also, of course, like a natural language processing or text analysis. What that means is, for example, if you talk to Siri in a more natural way, then Siri could understand you and still do things. And you guys probably also saw that Google demo that the machine learning algorithm, the AI, can make a phone call to schedule, haircut appointment for you. It's all meaning that the machine learning can understand human language. Human language is really fuzzy and uncertain, but nowadays, with the accumulated data, machine learning started to learn the features of human language and get the internal structure and knows that. Speech recognition. So there are a lot of online use of that, like if you talk to the computer, it recognizes it's you, not somebody else. And they can even do the opposite. They can just fake your voice or even fake your video. I don't know if you guys have watched that video on YouTube. It's called a deep fake. So you can definitely Google that deep fake. They just get like some video streams from President Obama, and you can definitely fake the speech, the sound, the voice, as well as the entire video. Let me see if we can find something here quickly. You guys can see my screen. Oh yeah, not the entire screen. Let me just go share the complete screen.
Hey, good morning.
Now with former President Obama taking on fake news, except turns out it is not really President Obama in this PSA. This is a clear example of technology that could become more widely used. And ABC's David Wright is here with more. David, this video is proof that we can't believe everything that we see online.
That is right, Paula. Good morning. They say that the camera never lies, but technology is advancing so fast that it can lie with greater and greater effectiveness. And that's the point of this new video from Jordan Peele.
Our enemies can make it look like anyone is saying anything at any point in time.
Former President Barack Obama, right?
So, for instance, they could have me say things like, I don't know, Killmonger was right.
Wrong.
You see, I would never say these things, but someone else would. Someone like Jordan Peele.
Comedian Jordan Peele actually produced this video to warn about the future of fake news. The technology uses sophisticated artificial intelligence tools able to turn familiar faces, even presidents, into puppets.
Now there is software that can be purchased and done at home, and within a few days you can manufacture what someone says in a video.
Most people use it for harmless fun, like inserting Nicolas Cage into movies where he doesn't belong. But it can be scary stuff. Recently, hackers took this image of Parkland High School senior Emma Gonzalez tearing up a gun range target for Teen Vogue. They manipulated it to come up with a clip that appeared to show her tearing up the Constitution instead. Just the sort of nefarious use Jordan Peele and BuzzFeed, which co-produced the video, is warning about.
Moving forward, we need to be more vigilant with what we trust from the internet.
The message here that it's getting harder.
So you guys probably know PS, right? Photoshop, you can fake a picture, but nowadays it's more than that. It's actually faking the entire video and also the voice. That's machine learning, that's artificial intelligence. And also it is being helped, machine learning and AI are being used to help understanding the climate change, such as the prediction and weather analysis. And I think we talk about that. We are building very complex models nowadays to generate really, really accurate prediction. And also like a genetic science, that is a huge amount of data to be processed. It's very important for us to understand their internal structure, their internal relationship, and we want to cluster similar genes so we can understand their functions together. That's something called clustering analysis. It's very common in genetic science. And also we can use this machine learning algorithm to understand how protein are folded. So we can discover new proteins, new medicines. And for civil engineering, machine learning is being used by researchers to detect construction workers, to detect the equipment, construction equipment status, and also try to predict the productivity and the final outcome of the project just based on all the data on the job site from the surveillance cameras, for example, and also like autonomous drones and vehicles, and also the four-leg pedal robots, the four-leg ground robots. Like Boston Dynamics started to sell their four-leg robotic dog since last year, and it's being used by construction companies, and it's fully autonomous and to inspect the construction activities and to scan the environment. So machine learning, AI, they are everywhere. So what is machine learning? I found this machine learning family tree online, and I found this is to be very comprehensive and holistic. So machine learning actually consists of whole bunch of mathematical methods. Some methods have a really long history, like for example, regression analysis. That group of method was actually invented about 150 years ago. But some methods were more recent and advanced. Probably you guys have heard about deep learning. That is a term that started to become popular, started to gain the popularity since 2005, so only about 15 years ago. And also like a Bayesian methods in general, that was also a really old method with long history, about 200-year history. So in general, machine learning algorithm includes this neural network-based method. So this one actually simulates how human brain works, not just human brains, but all the mammals. How the neurobiological system works, thinks, and predicts. So we learn from that. This is the bio-inspired method. Regression method, we will be talking about that in a moment. Clustering, this is one of what we call the non-parametric method, non-parametric modeling approach that without knowing, this is what we call the unsupervised method. So we don't have any ground truths, but we still want to review the internal structure of data. We run this thing called clustering. Do not worry if you don't understand what that means, because I'm going to talk about that and I give you some example. And of course, with the feeding of big data and with the data with really high dimensionality, we talk about that. There, we do have the tendency to add more and more variables to our model. And we keep increasing the dimensionality of our problem. So we are running out of data to feed into machine learning. So nowadays, a lot of machine learning algorithms, the step one is to do something called a feature extraction. Feature extraction is actually to give up on the raw data, but only focusing on the most important values, most important variables that represent 90%, 80% of the raw data space. We reduce the dimensionality to a smaller dimensionality so we can run machine learning. That's also a very important part. Bayesian and the decision tree, like I said, they are very classic 200 years ago. It's actually something called a knowledge-based system. So if we have some data, we have some prior knowledge about the distribution, like when it rains, what is the chance? So for example, in summer, what is the chance there will be raining? And if it rains, what is the chance that the lawn will become white? So if you have that established knowledge, and you can feed them into something called a conditional probability, right? You guys have heard about that, right? So if A happens, what is the likelihood that a B will happen? That's the conditional probability. So it's a very classic way to infer the status of a system based on the previous knowledge. That's a Bayesian and decision tree method. So in general, that's a really good map of machine learning algorithm. So we have to talk about the key concepts in machine learning. And after you understand these key concepts in machine learning, you will see, so even the map looks very busy, but in general, they just talk about this following 4 or 5 things. So this is another map showing another angle to look at the machine learning algorithms. Like we have this network-based method. We have this reinforced learning. Reinforcement learning means we try something, the algorithm try something, and if it doesn't work, let me try a different thing. So gradually it learns from the mistakes. This is very similar to how we learn how to ride a bicycle. This is very similar to how we learn how to drive a car. So we learn from the mistakes. That's called reinforcement. And we have this classic learning. We have this unsupervised, supervised ensemble method. And I have to say, this is a high level map of machine learning algorithms, but for each of the smaller boxes here, you will have a whole bunch of new methods. So for example, this neural network and the deep learning approach that simulates how human brain works. I found this graph online. This is called a neural network zoo. And as you can see, just for this, this is MLP, perceptual, and not even others, but just this one. This one can be this many. So just for a very small subgroup of neural network methods from this machine learning, you are also facing this many new methods, just different ways to organize what we call the neurons and also the axons, the connections. So it's still, I have to say, there are a lot of smart people from computer science, from statistics disciplines. They are also inventing new ways of making models. They are also, investigating new architectures every day. And we're still generating this, big school of machine learning algorithms. Okay, so this is the overall look of machine learning. You just need to remember, it's not one thing. It's a lot of things. It's a lot of mathematical methods. Some methods rooted from 200, 300 years ago. Some methods are more new. And in general, this is how we classify the machine learning methods. Parametric versus non-parametric, supervised versus unsupervised. We also have dimension reduction. This is more step one for most of machine learning. This is more the data preparation phase. We have the Bayesian method in general. So like a decision tree, Bayesian belief network, all those machine learning algorithms actually rooted from a guy called Bayes. Now Bayes actually invented a conditional probability. You guys probably have seen this one, P, when B happens, the likelihood of A, and then the likelihood of B. So if you want to calculate the likelihood of A, it's actually the conditional probability of that times the probability of B. That's Bayesian. But people after Bayes expanded his method to a whole lot of new level, like a connected network of conditional probability. We will talk about that. And also just recently, not recently, about 3-4 decades ago, people also discovered something called a descent gradient method, like how we can make a mathematical model to learn from the mistakes, such as how a child learns how to swim, like how they learn from the mistake and correct the actions, the motor actions. That is called reinforcement. So in general, if you understand these meanings, you should be comfortable of seeing all the machine learning algorithms. So let's talk about them one by one. First, parametric versus non-parametric. This is the official definition of that. So parametric models assume some finite set of parameters, theta, given the parameters future predictions x are independent of observed data. So what that means? That means that we assume that we have enough knowledge of that problem, and we can build a general top-down structure of that, such as a function. But one thing we don't know is the parameters, the coefficients of the function. So we just need to use the subset of data, which we call sample or observation, to feed a model. And then we should have a model to describe the future. Make sense? So this is called a parametric. So this is from the textbook, a very classic textbook, Artificial Intelligence, a Modern Approach, the definition. A learning model, parametric model, is a learning model that summarizes data with a set of parameters of a fixed size is called a parametric model. No matter how much data you throw at a parametric model, it won't change the demand about how many parameters it needs. So it's totally fixed. In contrast, what is a non-parametric model? Non-parametric model means, hey, this problem is too complex. I don't know what X I should feed into this model. I don't know what the model looks like. I even don't know the distribution of each factors I consider like X. So I treat it more kind of like a black box. And then I just design some very fancy way of one factor connect to another factor, one X connects to another X, and hopefully this magic black box will give me an answer. So in that way, we are talking about a potentially infinite dimension gamma. That means we even don't know for this function y equals to fx, how many x I should consider, or how many data sample sets I should consider. So there's no function in a sense. That's called the non-parametric modeling. So from the same textbook, non-parametric methods are good when you have a lot of data, but no prior knowledge, and when you don't want to worry about too much about choosing just the right features or the right X. Okay, so I'm just giving you an example, regression analysis and artificial neural network. Regression analysis is the most representative parametric method in machine learning, and artificial neural network, or ANN, is the most representative non-parametric method. So I decided to use these two examples to show you what's going on. So regression, this is a very interesting history. Charles Darwin, you know this guy, right? He wrote the book, The Evolution. So he invented the evolution theory. His cousin is called Francis Galton, and the Galton's student is called Carl Pearson. And these two guys actually invented this regression method. And Pearson also invented something called the Pearson correlation analysis. Have you heard about that? It's the correlation analysis showing that A and B, it's a number showing that how relevant they are. And this number ranges from -1 to +1. If two things are more positive correlated, it's probably like a 0.6. If they are more negative related, then you probably is expecting -0.8, right? So that's called a correlation analysis. So think about that. This very interesting regression analysis method, the most important one, is also somehow related to Charles Darwin. It's this very interesting history. So why we call regression? Basically, Francis Galton discovered a phenomenon that if the parents are taller, their children are usually taller. If the parents are shorter, their children are also usually shorter, okay? So from a biological perspective, he called this phenomenon regression, which means we, the children, regress to the features of our parents, okay? And then his student, Carl Pearson, got this framework and developed a mathematical method to describe that. So this is called, he calls this regression analysis, but the meaning is totally different after that. It's more related to a pure mathematical model to describe the relationship between two things. Okay, so what is regression analysis? So let's say if I have two variables, one is called an independent variable, one is called a dependent variable, X and Y. And let's say X is your GPA and Y is the salary of your job, okay? So let's assume this there's a relationship that if your academic performance is better, then you will find a better job and your salary is higher. You guys agree? So that's a reasonable relationship. And let's assume you have the knowledge, which means you know this thing. That's called the known, right? And let's assume you know there's a coefficient called 0.5 to convert your GPA into your final salary. Of course, we can change the unit, right? Let's say it can be maybe, let me change it to a different number. So maybe, your GPA ranges from, 1 to 4. And this one shows your monthly salary. So if you receive a 3.0 GPA, your final salary would be $15,000 a month. So let's assume if you know the fact, if you know the truth somehow, from the gut level, you know that, then you have a function to describe that. Make sense? But in real world, unfortunately, usually the problem, usually what we have is this. We don't have any existing model, okay? We don't have an existing model, but we are making something called observations. So it's kind of like I'm surveying, hey, I'm saying, Remy, what is your current GPA? And when you get a job, I asked you to share your salary with me. So I got a data point for maybe you're here, right? And they asked it, hey, Eric, what is your GPA when you did your graduate, when you did your master degree, and what's your current salary? So I got another data point. So can I still find a formula to describe the principle of this, or to describe the underlay, rule of that? Yes. And how we do that? We find the line. Is this the perfect line for it? It is the perfect line for it. Or is that the perfect line for it? So we need to find the line that is the most balanced and unbiased description of data. So can anybody tell me what that line should be?
I think it should be the higher line.
Should be the higher line? I'm
I
talking
guess-
about the higher line actually,
Right.
That's the interesting thing. Higher line actually represents the best people. With giving GPA, we actually received, the salary higher than others with the same GPA. So this is actually another type of research called the DEA, data envelopment analysis. But I'm talking about what if we need a line to have the most unbiased and the most balanced view of the distribution of data or the relationship between Y and X.
I guess
I think it's a middle one.
So the middle one. So the line that goes through the center of most data, correct? Yeah, so let's do this. Let's say if we have 4 data points from 4 students of the class and we want to understand the relationship so we can make a prediction. What is the best line? I feed this line. And I know, I assume a function called y equals a times x. I just don't know the slope of this line, right? So this is the coefficients that I don't know. I need to find out. So, then I can calculate the error, the mistake, right? So I have this line. I have to have one line. And from the observation data 1 to this one, I have this arrow delta 1, and this one delta 2, this one delta 3, this one delta 4. So to evaluate how good this line is, should I calculate the sum of the error? No. Why? Because we got some positive arrows and we got some negative arrows. If you just simply add them together, then the positives will cancel out the negatives, correct? So what is the best way to do that? We square them and add them together. Make sense? So this is called the sum of squared arrows. So it's very simple. This is the most common way in mathematics to convert the negatives into positives, right? So we just put a simple square to 1, 2, 3, and 4. And then this is called SSE. So this is our line, but we need to compare it with something so we know how good it is. This is the absolute arrows we have, but what is the baseline one I can compare against to see how good I'm doing, this line is doing compared to some line. Let's talk about the voiced line. The voiced line means nothing, means zero information. In this case, it's level line, which means I don't give you any information about your future salary. I only know your GPA. And this line to describe this phenomenon is the voiced line. Make sense? So now I calculate if I only got the voiced line, what is the arrow from point A to the voiced line? That's called T1, T2, T3, and T4. And let's do the same thing. I square them up and add them together. That's called the sum of squared total, okay? And then I use this SSE divided by the sum squared total, which means compared to the voiced line, how much better I am, how much I improved from the voiced line in terms of predicting the relationship between X and Y. Make sense? And this is just a common practice. I don't know why, but the people tend to convert this number to a bigger number. Usually a bigger number means better thing. But think about this one. If we use this function, a better line always give you a smaller SSE over SST. Make sense? The most perfect line will give you what? 0 SSE. The most perfect line means I just perfectly predict the position of each data point. So my SSE is 0. But usually we want to do the opposite. So we just use 1 minus that. So then we can just convert that into a number that's called R square. Okay, the R square is a number from what to what? Let's say the best situation SSE equals to 0, then 1 minus SSE over SST equals to what? Come on, guys, anybody? One, right? Say something, guys. And then the voiced situation is what? SSE is SST. So if I, somehow I couldn't find the blue line and the line I have is the right line, then SSE is equal to SST. Then the voiced R square is what? Is 0. Makes sense? So it's 1 minus 1. Then R square becomes something called the goodness of fit. Okay? So 0 means the voiced goodness of fit, and 1 means the best goodness of fit. Okay, and that's actually one simple situation. That's one-dimensional y equals to ax. What if I have 2x? Let's say this is your GPA, but this is your years of internship, okay? And we know your GPA and years of internship, if you also decide your final thing, it's okay. Instead of finding the best line that goes through most data, we are just finding a 2-dimensional plane that goes to the most of data. Make sense? We're just basically expanding the same mathematical concept from 1 dimension to 2 dimensions. And of course, I can find the distance from the data points to the 2-dimensional plane. I can do the same thing calculating SST and SSE. But this time I know the formula would look like y equals to a times x plus b times y plus some kind of error term. It's noise, but the principle is the same. R squared still equals to 1 minus SSE over SST. This is called regression analysis. Okay, guys, why I say regression analysis is a parametric method? Because even though I don't know the value of the coefficient, but I'm pretty confident the relationship between y and x should follow this structure of model. I know how the model looks like. I just don't know the exact value for that. So I collect data to find out the value for A. And similarly here, I'm pretty confident y should equals to ax plus by. I just don't know what the value for A and what the value is for B. So I collect data to find it out. So the key point here is I know the model. I just don't know the values for each coefficient. This is called a parametric modeling. Make sense? This is actually what we also one of the machine learning algorithm. A common misunderstanding is, people tend to call this thing, linear models, but this thing called nonlinear models, because sometimes, we have this formula or we have the knowledge like y should be equals to something times the square of x. For example, in this case, your GPA is probably more important. So I can give it a square. I know, if you improve your GPA a little bit, your fellow salary increase a lot. So I know there's a square here, okay? In fact, this is also called a linear model. Why? Because we can create some dummy variable such as x3 and let it equals to x1, square. Then I can convert mathematically this formula into this formula. Make sense? So mathematically speaking, they're still linear modeling. But anyway, this is called, parametric. So what if we cannot find a function, or we are not confident at all with assuming a function in advance? So for the same thing, I know, hey, your final salary depends on your GPA and also depends on your intern experience, maybe depends on other stuff. But we don't know how the relationship should look like. I'm not confident of giving this dummy function to describe the relationship, or from my experience, I know the relationship is very complex, something like this. Actually, this is the real data I collected from the industry. In this way, what can we do? Now, this comes with the other side of a method called non-parametric Bayes-inspired method artificial neural network. These two guys were the inventors of them, Warren McCulloch and Walter Pitts. they basically discovered that the general principles that how our brain thinks and uses that to create some black box to make prediction. So how our brain thinks. You know, we have about 100 billion brain cells and 20 or 30 times more connections. So each brain cell is connecting to about 20 or 30 neighboring brain cells. And each brain cells is very simple. The function is very simple. They're only doing receiving and sending. So they're actually receiving electrical pulse. And what they are doing is just doing the addition. So let's say I'm connecting to 20 brain cells, and the 10 brain cells are somehow sending an electrical pulse to me. And I just basically add the pulse together. I got a number, like a voltage, and I compare somehow to a threshold I have. And I make a decision if I want to send the pulse or not. So if the summation of the pulse I'm receiving are smaller than the threshold, then I will keep silent. So the brain cell will not send the pulse. But if the pulse I'm receiving are stronger than my threshold, I will send the pulse. So I'm basically passing over this pulse to the next one. So we just keep doing that, and magic happens. By the end, we can predict things, or we can learn things from that by doing something called a parametric adaptation. We change the value of the parameters, the important parameters. So let me show you this process really quick. So let's say I have these are called brain cells, the brain cell layers, okay? And this one also brain cells. So this is input, and these are 3 brain cells. So we got 3 brain cells here. These are our inputs, and this is their calculation, and this is output, okay? So what it does is each brain cell is receiving, some input from other brain cells and add them together, but they also compare it with some threshold. Usually the threshold is not linear, it's S-curve. And they make a decision if you want to send it or not. And meanwhile, the brain cells have different level of trust, different level of trust. So like they gave it weights to different brain cells. This is like a gossip network. Your friends are sharing an interesting story with you, but you can decide how much you would believe. For a certain friend, you give them 100%, but for a certain friend, you give them 20%. So basically, this is a weighted summation. And finally, you give this one. So let's say, I'm trying to predict the cost of a construction project based on some project parameters, like who the project manager is, what the construction equipment are used, the type of concrete being used, okay? And then at the beginning, I just randomly assign the weights to each connection and randomly pick a threshold and try my best to give an output. And then I compare my trial against the real output. Of course, I know it's not the same, it's not perfect. So I send it back and I say, hey, everybody, every brain cell, please adjust your weights. Please adjust the threshold, and let's try it again. And just keep trying, guess what? Finally, the right combination of the parameters, the right combination of the thresholds will generate a y prime, the predicted y, very close to the actual y. And this is called artificial neural network. This is how you guys learn how to ride a bicycle, how you guys learn how to remember a person. This is what's happening right now in your brain. Each brain cell is doing this kind of a calculation, addition, and adjustment, depending on what task your brain cells are working on. Make sense? And this is a quick metaphor of that. Actually, think about 3 brain cells can do a lot. I'm going to show you quickly example, and think about actually each person has more than 100 billion brain cells and so many connections. That's why we have this magic tool to change the world, to understand everything. So let me show you quickly how it means, okay? So now I have this data. You guys can see my screen, right? Okay, now I have this data. It's actually different project. That's all power plant project. And this one shows the megawatt rating, which is, the size of the power plant, like how much power it generates. And this one shows what is the type of the job, what the engineering company and what's the configuration look like in terms of turbines and the generators and blah, blah, blah. And also some distance between the important equipment, mechanical equipment. So I got this thing. So let's say what regression means. So I'm just going to do this one. So let's say I want to predict the distance. What do we call outside stack distance? Basically shows that the total distance that I need to run the underground pipeline to connect the major components. And also megawatt rating as X. What I mean, I want to see if I know the megawatt rating of project, can I know, the total distance I would need for my underground pipeline? Make sense? So now think about what's this? Is this parametric method or non-parametric method? Anybody?
Parametric.
Exactly, because I'm assuming y equals to ax. Makes sense? Now I just need to find a. And from this graph, you can see it makes sense, right? So the bigger megawatt rating means like a bigger distance. So let's just feed the line. So I found this line. The line goes through the most data, and I got the R squared 0.61. You guys understand how we calculate R squared. And this is the formula. 0.47, and this is the constant term of that. So, but think about this. I already, before I run this model, I already assume this distance equals to something plus something times megawatt rating. So this is totally parametric. Make sense? Okay, so if I run like a multiple, can I run like a multiple x, like y equals to x1 something times, plus something times x2 plus something times x3? Yes. So let's say I still want to predict this st, but I also want to check this megawatt rating and maybe number of equipment and maybe cooling tower cells. So let's say y equals to something like a x1, 2, 3, and I run this one and just run feed line. Okay, sorry, this is, I should have used a different one. Okay, so let's say I still want to try this one, but now this time I want to put multiple X here, okay, and just run. And I got a big model here. Let me show you where the model is. Doesn't show. It shows the parameter here, but it doesn't show the model. I want to show you guys how the model look like. Let me see. Should save prediction formula. So this is formula that it found out. It's something times megawatt rating, something times equipment, something times cell plus a constant term. Once again, 1x multiple x is the same thing. We assume a function. So this is in advance. This is called a parametric. So what is non-parametric? Let me show you. It should be here, okay? So let's say, once again, I want to predict the total distance based on, the things I have. I'm just going to select maybe many things here. But this time, I don't assume any function. I add neurons. So I basically use the neural network. So in this case, I just gave them like 3 neurons to predict and just say go. And I got the R square, similar R square, 0.81. So usually it's better than the regression method. And how to visualize that? This is how it looks like. Now make sense? These are the 3 neurons, and these are the inputs, and this is the predicted out-stack distance. So it just happened so fast, but it actually repeated for more than 1,000 times, adjusting the weights of each connection, the threshold comparison. So think about this, guys. Can I write down a formula for this thing? No, there's no formula. It's a black box. It's a magic box. And this is the artificial neural network. Nowadays, a lot of machine learning algorithms are based on neural network. So deep learning, it just, you have so many layers, so many additional steps of repeating this neural network. All different approach to simplify or revise or process the input, but ultimately it's a neural network structure. That's why you probably have heard about that. Machine learning or artificial intelligence is a black box. That's why, because there's no way for us to write a formula to describe that. It's more of something staying there and then the magic just happens. Make sense? So this is the first important concept in machine learning, parametric over non-parametric. I'm going to cover the supervised versus unsupervised very quickly. And then my PhD students, Judy and Tianyu, will give you some more advanced machine learning examples that related to their research right now. But you will definitely see their root is nothing but just regression and a neural network. So the general principles remain the same. Okay, so what is supervised? What is unsupervised? So if you're learning a task under supervision, someone will present the judging whether you are getting the right answer, the ground truth. Similarly, in supervised learning, that means having a full set of labeled data while training an algorithm. Okay, so basically you have ground truths. Like say, I'm teaching a machine learning algorithm to recognize this is cat, this is dog. So you're giving them a lot of pictures, which we call tagged pictures or labeled pictures, because while I'm giving them the pictures, I'm telling them, hey, these are cats, these are dogs. I tell them the ground truth. So they learn from there, and that's called a supervised learning. It's kind of like when you're teaching the small kids, oh, that's a dog. You are keep telling them the ground truth. So they build that model gradually in their mind. That's called a supervised learning. So what is the unsupervised learning? A lot of times labeled data sets are not easy to find out. So we don't have any labels and we don't have any explicit instructions on what is right, what is wrong. The model, the machine learning model, has to try a way to cluster the data based on the feature, based on the similarity. And hopefully by doing that, we can discover something in common, some common features. That's called unsupervised learning. And basically, it refers to classification or clustering. Supervised learning, we often call them in machine learning literature, classification problem. Unsupervised learning, we often call them clustering problem. So for example, when we feed the model with pictures of apples, I also tell them, hey, these are apples. Then I gave this machine learning model a different picture of apple, and the task is to recognize this is an apple. This is called a supervised learning, because when this model predicts, oh, this is a peach, I would say, no, it's wrong. And until it tells me, maybe it's an apple, I say, yes, correct. So just keep doing that until the model knows, oh, this is the right feature I should focus on. If this dog is fuzzy with 2 eyeballs, it's so cute, it must be a dog. So it learns the feature, that's called a supervised. But unsupervised, unfortunately, I just threw a whole bunch of pictures like apples, peach, and bananas to this model. I don't tell the model anything, but the model just say, hey, just try to cluster the data, try to separate the data based on something. And they are usually good by grouping the apples together, the peaches together, the banana together. And hopefully by doing that, next time they can figure out a way to say, oh, why they are different. That's called a supervised over unsupervised. So let me show you this example using the same data set I have. So once again, I have a lot of projects, different macro rating, different job type, different engineering company. Now let's try unsupervised first. I don't tell anything what I want to do. I just say, can you somehow find the similarity in data and tell me, how you would group them or cluster them? So let me just say clustering and go k-means. So I'm going to just put everything here. And I just tell them, maybe try to group the projects into 3 groups, but why the 3 groups, I don't know. And it did that. Let me show you how it looks like. See? So basically, I don't know what they want me to do, but if I plot them, somehow I see certain projects tend to come together. And I can find a project representing the group of them. So I try to group them into 3 groups according to the instruction, but I don't know why it's 3 groups. And by the way, guys, you see this is called a PC1, PC2. This is a principal component 1, principal component 2. Why? Because think about the numbers, the variables I use to group the projects 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is what? 11 dimensionality. Can we see 11 dimensions? No way. So this one is called a dimensionality reduction. So basically, imagine you are able to see 11 dimension things. You are 11 dimension creator, okay? But you have this high dimensional camera. So you can take a picture from a certain angle, and the picture is still 2 dimensions. And this principle 1, principle 2 means what? You'll find at a certain angle that separates the 3 groups to the most. And you think that's the best angle for me to take that picture. You take that picture and that's how it looks like. So this one you are seeing on the screen is actually a 2-dimensional picture of that 11-dimensional thing. Make sense? Can we create a 3-dimensional picture because this is 11? The answer is yes. This is how the 3-dimensional picture look like. But think about this is projection from that 11-dimensional space. Make sense? So this is what, once again, this is unsupervised learning because I don't tell anything about this one. But what if I have something, for example, RIR. Safety record, okay? What I mean, RIR means recordable incident record. And that means, how many incidents happen in this particular project. So the higher IRR means what? Means a worse safety record of the project. And we know somehow the features of project somehow relate to their safety records, right? So do we have that data? The answer is yes. So we do have that data. Okay, so now let's say I tell this model, hey, given this combination of these parameters, the safety record of the project was good, but given the combination of the parameters, the safety record of the project was bad. Now, if I give you a new project, can you somehow predict the safety record or classify this new one into either the good, medium, or bad? So think about that. I already tell something to the machine learning model, kind of does that. So let's go to this method. This is called a supervised learning, right? So basically I just tell them, hey, these are the known categories, okay? And based on all the things here, can you classify them into the categories? And this is how it looks like. So basically this one shows good, this one shows medium, this one shows bad. And if there's a new project going on, and it will basically be a point on this figure. So by comparing this, where the figure fall in, I know this project will be a bad, medium, or good project in terms of safety record. Because I already labeled the data, I tell them what's going on. This is called a supervised learning. Make sense? Question, guys. Once again, we have 10 dimensions to classify the product into different safety record categories. But why we only see 2 dimensions here? What happened? Anybody?
The dimension reduction.
Exactly. So we reduced dimension. We took a 2-dimensional picture out of the 11 dimensionality. Can we do 3? And the answer is yes. Let me see if we can find it. Huh. No, I cannot find it now, but you guys know the concept, right? So this is actually, and I see the misclassified is only 2, which means, oh, this model is pretty good, now it's pretty smart. So if I feed in the, like if I got a new job here, I just put the numbers here, you know what, this model is so useful. It tells me the likelihood that this product will have a good record, safety record, or bad safety record. This is called a classification. So we just covered 2 fairly important things in terms of machine learning, which are parametric over non-parametric models and supervised versus unsupervised model. So if I go here, let me ask a quick question before the break. Regression, is that parametric or non-parametric?
Parametric.
Parametric, because we assume a structure of the model. Deep learning, that parametric or non-parametric?
Non-parametric.
Non-parametric. A difficult question. Bayesian method, is that parametric or non-parametric? Remember, Bayesian assumes a lot of conditional probabilities. It is parametric because you assume you know when A happens, the chance B will happen. You also know A and B has some kind of connection. That's parametric, right? Okay, so in terms of supervised and unsupervised, let's say clustering, is that a supervised or unsupervised?
Unsupervised.
Unsupervised. And let's say neural networks, is that a supervised or unsupervised? That's usually supervised because you ask that to predict something, which means you remember you provide the true answer, the ground truth, and ask it to compare with the ground truth. So you are telling it the ground truth. Make sense? So it's kind of like you are teaching a kid to swim. You are telling them, oh, no, you shouldn't move your hand in that way, you should move this way. And they are correcting their behaviors to mimic your behavior. So that's definitely supervised in most cases. Of course, there are some exceptions. Let me find another one. Let's say decision tree. Is that supervised or unsupervised? Decision tree is very similar to Bayesian. Basically, when something happens, that thing will happen. Something doesn't happen, this thing wouldn't happen. So decision tree, is that supervised or unsupervised?
Supervised.
This is also, this is what?
Supervised.
This is supervised because we tell, usually the way we find that right decision tree structure is to tell it if the final classification is correct or not, right? Yeah, you can imagine this is a classification method as well. So, and of course, dimensionality reduction, we also cover that a little bit, you know, like how you see the pretty simple component census PCA, you know, it's kind of like we have this high dimensional data. I want to visualize that all. I want to simplify the data to fit into my regression model or artificial neural network model. So I basically take a picture of the raw model, but I still keep the most feature, the most structure of that. That's called the dimensionality reduction. Okay, so this is really quick overview, introduction to the most fundamental disciplines, principles of machine learning. So let's take a 15-minute break. Let's return at 5:40, and then Judy and Tianyu will introduce a more deep learning approach, nowadays deep learning approach, but if you see, they're actually rooted in a lot of fundamental machine learning algorithms. Okay, see you guys then.